Hi everyone, my name is Wagdy. I am researcher and lecturer at Queensland University of Technology, as well as I'm senior lecturer at University of Queensland and researcher as well at CARSQ. I just passed my PhD examinations and got nominated for Outstanding thesis Award, and this paper is one of my contribution during my thesis. I would like to share it with you here in Playa. I'm looking forward to share the knowledge and also the tools that I developed through my PhD. Machine learning in glare analysis. I'm proposing a new framework for glare prediction in open plan offices using machine learning techniques. To give you a bit background about the topic, this research is funded through an ARC linkage project. The key points we collected from literature review is daylight is very beneficial, and it has many advantages and contribution to the well-being as well as to the performance of the building itself. However, too much light become a problem as it can produce glare. So in order to develop metrics for glare prediction, what we need to do is to collect data using HDR images and correlate it with a survey. The main idea is to match the subjective judgment of glare and correlate it with the output of glare equations. Usually, glare equation is consisted of 4 elements, which are the luminance of glare source, the size of the glare source, and background luminance, and where is the position index. There is a lot of metrics were developed since 1950. However, in UGB was developed in 2014, and it's the only metric which is developed specifically for open plan offices, which is my area of research. However, the performance of the metric was not adequate in open plan offices because we found that it has an overall accuracy of 69%. So why do we need to introduce a new methods for prediction glare? Because we found the current method for developing metrics is not covering very well the open plan offices as it differs from the cellular offices, the low luminance and the contrast-based glare. So the idea here is to try to use machine learning integrated in the glare prediction methods in order to cover this aspect. In order to conduct this research, what we need to do is to have a real or true labeled data. To get the true labeled data, we collected data from different 4 open plan offices, tried to capture the luminous environment while people are there. So we proposed a way of calibrating the phones with fisheye lenses in order to have an adequate performance that can be used later on with data collection or with glare analysis. So the idea, we done photometric calibration in photometric lab where all these results and parametric calibration methods were published in this paper, as long as a tool that allow other people reproject the image in different spherical projection. Then we calibrated the images from the phone for the camera response function and vignetting correction as well, using a range of different color temperature and different lighting environment. Then we started to extract the luminance information in something like a superpixels, and then we can compare the luminance between this region and each other. This way, it can produce like more useful maps, like the one on the right, in which it allows the machine learning algorithms to understand very quickly where a problem happens due to glare and how much is the severity between the contrast between these regions. So the paper we are presenting here, has a larger version which is available on the preprint, have an extended information about the methods based on the machine learning algorithms we have done here. So to give you a sense how people usually develop a threshold in which they can relate to one of the glare metrics that are already existing and define which number is higher than a threshold, it become like a glare situation. If it's lower than that, it will not be a glare situation. So if we analyze an image like that, and we talk the DGB, for example, we can see that this number is now 0.27. So if we start to say, okay, do we have a threshold from 0.1, means there is no glare. Once we got to 0.3, we can say it's become a glary situation. So this is a way that we can define the threshold And we can draw this graph on the right using the ROC analysis, which is a trial that we have made so far here. We done the same seed procedure over and over for all glare matrices. We're using 5 k-folds across validation scheme. And based on that, we delivered these thresholds here, the numbers in the black dashes that can be used for open plan offices. So that's why we have very lower number here. But as you can see here, there is no a single number that can distinguish between glare and non-glare, as two numbers or the two categories are ranging from almost top to bottom, and these are representing all data that we collected. So we tried to compare what we have if we are using ROC analysis as well as the k-folds method or other matrices failed to pass the overall accuracy of 70% at least. So going here, which machine learning methods that we aiming to use, the choice is based on the number of training data available. So what we have done, we tried to compare between current statistical methods and using 5 k-folds to treat the machine learning as we treat the statistical method. And in the machine learning, we use the glare scores from each glare matrix extracted from the detailed analysis using EVA-glare as a feature for learning the glare potential in each image. And we tried to use the multi-region methods, the ones that I just showed you before. Okay, and then we used more than 25 machine learning algorithms and classifier in MATLAB in order to check which one has the most accuracy over all of them. And then we put criteria for defining that we need at least have overall accuracy of 70%, which should be higher than the current glare metric UGB. And also we need to make sure that the TPR and TNR is above 0.5 in order to eliminate any random decision. So starting each one of the glare matrices as a feature was not that useful in comparison to the multi-region methods. So here is a multi-region method. We explored the performance of 7 sizes starting from 10 by 10 until 40 by 40. So we can extract and reevaluate the luminance average of each of these regions. And we use all these images in order to train the model. So we have a folder of HDR images. We allow machine learning which help us to predict the glare and non-glare situation with an overall accuracy of 84%, which has true positive rate of 0.8 and true negative rate of 0.86. We summarize all information that we collected from the different machine learning algorithms and the different features used for training the algorithm, and we also combine different metrics together, the 24 metrics together as features, as a group of features, or 6 glare matrices, which are the default output of EVA-glare, and we compare it with the machine learning ones considering the multi-region methods. As you can see here, this is the best machine learning model using Ross tree. And once we try to compare it with ROC analysis, we can see just the luminance background is the only metric which achieved better than all ROC analysis in all other matrices. So the idea of using the Open Plan Glare Evaluator, OGE, that you can use your simulated HDR images or the captured HDR images within existing buildings and run the OGE analysis in order to check the probability of glare or non-glare situation. And these are like all the key papers referenced in the paper itself, which has more details about each step if you'd like to. Thank you so much. I hope you like my presentation and wish you to use this tool. The tool is free and it's available in GitHub. Please have a look and feel free to contact me again if you need to have any information. Thank you so much.